Good morning everyone, hope you're all well. It's Dr. Bennett here, and today we're going to look at an extension of what we were looking at last class, which is about drawing diagrams for our internal forces of members. So this is section 10.2 from the textbook, starting on page 493. So you'll recall from last class that we were looking at internal forces of a member, and we did this example here where we found the axial force, the shear force and the bending moment at a specific point along the member, in this case at point C, right? And how we did that was we made some cuts along the member at point C, right? And then we found the axial force, shear force and bending moment at point C by applying the equilibrium equations to either side of this free body diagram system, where we have the left hand side and the right hand side. So that was fine, but that only told us what was going on specifically at point C. What we would like to do today is work out what's happening along the entire length of the member. So what happens when we move point C around, and can we make a visual representation of how these internal forces are changing along the length of the member? So that's where today's class comes in, right? We're going to be looking at drawing like graphical depictions of how these three things change across the length of a member. So we're going to discuss this in the context of this example here, which is similar to the one that we had in the last class. So we have a beam in equilibrium, we have a force of 1/3 F applied in the upwards direction at A, 2/3 F applied in the upwards direction at B, and then F to balance these two applied downwards, but at some length along the member, so two-thirds of the way along from point A to B. And the question is to show how the internal forces, namely the axial, shear forces and bending moment, change along the length of the member. So, instead of cutting the member at a specific point, C, like we did before, where we had an actual dimension associated with that, we're going to cut the member at an arbitrary length X, right? So that when we draw our diagram, we can change the value of X to show how the internal forces change along the length, right? So we don't give this a specific length right now, we just call it arbitrary length X. And we need to make some cuts along the member to show how the internal forces change with X. And we need to make these cuts between externally applied forces, because you can see if we cut the member somewhere here, and if we cut the member somewhere over here, this externally applied force F is going to change the magnitude and direction potentially of these three forces within the member. So we need to make one cut this side and one cut this side to show how this F changes what's going on inside the member. And that's what I've described here. I'm going to make one cut at a distance X, somewhere between 0 and 2/3 L, so 0 and 2/3 L, and then I'm going to make a second cut between 2/3 L and L. So basically a cut this side of F and a cut this side of F. So what I've done here is drawn free body diagrams of those two situations. Look, I've got X defined between 0 and 2/3 L, and I've made a cut at a point C, which is at a distance X away from A. So that's somewhere between A and where F is applied, right? And I've labelled my axial forces, shear force and bending moment in the same way as I did in the last class. And what I can do is solve the equilibrium equations for this sub-free body diagram like I have over here in the usual way, to find the unknown internal forces P, V and M. And I've done exactly the same thing, but now I've made a cut here between F and B, right? So I've drawn the free body diagram the same way, but this time I've included the force F, and I've cut the member at point C, which is now on this side of F, right? So again, I'm calling that arbitrary distance X from A to C. And again, I've gone ahead and solved the equilibrium equations now for these unknown internal forces, and I get the following solutions. So you'll notice that here M depends on X, right? So that's kind of a linear function of X, so that tells us how the bending moment changes as we go further along the beam. So at this point, 2/3 L, the value of V and M are going to flip to something different, right? So what I do to show how that works is I draw how those three internal forces, axial, shear and bending moment, changes as X increases from 0 to L. So over here, look, I have the axial force is 0 in both situations, so all the way from 0 to L, P is always equal to 0. So that diagram is very easy to draw, right? And that's obvious that there's no axial force, right? Because all of my forces in the original diagram are perpendicular to the member, and remember, an axial force is along the axis, right, of the member, like in a truss, for example. So that makes sense. The next thing I draw is the shear force and how that changes as X increases. Well, between X equals 0 and X equals 2/3L, I have the shear force to be equal to 1/3 F, minus 1/3 F, sorry. So that's just a straight line up to 2/3L. And then after 2/3L, it's equal to 2/3F. So that's just another straight line up there. So then I just join up my pieces and how that flips at the value 2/3L, and that's my shear force diagram. And then finally, I've drawn what happens with the bending moment. So a little bit trickier to draw, but if you just consider what happens at the end points and then draw them together, you know these functions are linear. So at X equals 0, M is equal to 0, right, from here. So I have this point. And then at X equals 2/3L, I can work out what M is by putting that value into either this formula or this formula. I should get the same answer, and that is 2/9 F times L. So I've drawn that positive value up there, and I now have this point. And then finally at X equals L, if I put X equals L in here, I get M equals 0 again. So then I have this point, and then I can join the dots, and I can see that the bending moment is maximum at the point where F is applied. And again, that's intuitive, right? I should have maximum bending at the point where the force F is applied. So that's just a an initial quick example of how to draw these axial force, shear force and bending moment diagrams. Alright, so now let's have a look at a slightly more complex example. We're going to have a look at example 1038 and 1039 from page 498 from the textbook. It's about an aeroplane, so you know I like to talk about aeroplanes wherever possible. So it's a slightly more complicated example of what we've just seen because it involves a few techniques of what we've seen over the last week or so, namely this distributed load, so the lift of the wing has this profile, and also combining that with our axial force, shear force and bending moment diagrams. So we're going to analyze this problem here. We're looking at basically the lift profile of one wing of this aircraft. We have some dimensions. We have the weight of the wing, well, weight of the engine acting at this point here, and we're given the magnitude of this part of the lift profile at the wing root. So essentially we have this situation here. We can find basically a force vector by finding the area of these pieces of the distributed load, and then we can find a centroid of that area to give us the position where that force vector is acting. So that's what I've done here. I've basically found the area of this rectangle here. It's 4.4 meters long, right? And the magnitude of the distributed load is 50 kilonewtons per meter. So that gives me a force of this piece of 220 kilonewtons, and we know that the x-coordinate of the centroid for a rectangle is just halfway along it, so that's just 2.2 meters, right? So that part's fairly straightforward. Then if we look at the triangular section, again we can find the area, half base times height, right? So half base is 13 meters. The height again is this piece, is this side here, which is 50 kilonewtons per meter. So that gives us a force of 325 kilonewtons. To find the x-coordinate of the centroid of this triangle is slightly more complicated. We can look up our standard results from the textbook for a triangle. So if we flick back to Appendix B for a triangle here, look, page 578, we can see that the coordinate of the centroid is just 2/3 from the small end, or 1/3 from this side. So 2/3 of 13 gives us 8.67 meters, but that's the result from the right hand end. So we just need to flip it around and say that the x-bar coordinate of the triangle, if we take the mirror image basically, is 17.4 meters, which is the total length of this. Subtract this value that we've just found and we find 8.73 meters from the wing root to the x-coordinate of the centroid, so it's around here somewhere. Okay, so now what we have is basically a force vector and a location for those force vectors due to this distributed load of the lift profile of the wing. So we can go ahead now and draw a free body diagram of the wing with all of the forces acting at the known distances from the wing root, which I'm calling A. So I've got a fixed support where the wing touches the fuselage, so that means I have a reaction in the x direction, reaction in the y direction, and a moment. And then this is the weight of the engine that I was given in the question, remember? And then I also have a force vector acting here and a force vector acting here that I can draw on to my free body diagram. So those are the two force vectors that we calculated above due to the distributed load. So what I've done is just basically found the x coordinate of the centroid so that I can put on these force vectors at a known distance from the fixed support at A. So I can apply the equilibrium equations to that, which is what I've done down here. The x direction, I just have FAX, so that's 0. In the y direction, I have positive this, negative this, positive this. So therefore I can work out the reaction in the y direction at A to be negative 465 kilonewtons. And then if I take moments about A, I have a positive MA plus a positive moment due to this force vector, negative moment due to this force vector, and a positive moment due to this force vector. So I have 4 terms in the sum of the moments equation, and I can find out the moment due to the fixed support at A. So following that, we need to start to look at the internal forces acting on the wing. So as we've just discussed in the previous example, we will make 2 cuts either side of the external forces. So I'm going to make 1 cut here somewhere, and I'm going to make 1 cut here somewhere. I'm going to draw on my unknown internal forces. I'm going to apply the equilibrium equations, and then I'm going to find the axial shear forces and the bending moment. So that's what I've just summarized up here. But now I need to go back to consider my distributed load as a function of x. Now this is a very, very important point here. So to get to this point of the solution, I found a single force vector acting at the centroid of this distributed load. But obviously when I consider a cut somewhere between x equals 0 and x equals 4.4, then I don't have the same distributed load, right, because I've chopped some of it off. So I now need to go back to consider the distributed load as a function of x. Hopefully you can all see what I'm getting at there. Just to explain that once again, if I make a cut through the wing here somewhere, I've chopped off some of the distributed load. So therefore I can't consider my force vector acting in the center anymore, because it's not a total distributed load anymore. I've chopped some of it off. So I need to consider this distributed load as a function of x now. So I've drawn my 2 free body diagrams. So I've made 1 cut before the weight vector due to the engine, and I've called that distance x from the wing root A. And then I've drawn on my unknown axial force, shear force and bending moment. And then I have this distributed load as a function of x. So the magnitude is 50 kilonewtons, so the area here is now 50 kilonewtons per meter multiplied by this distance x, which I'm leaving arbitrary as in the previous example, so that I can plot how these forces change as x changes. And then I've put on my reactions at A that I've just calculated by evaluating the equilibrium equations to the whole system, right? So this looks complicated over here, but we're just following the same rules as we have done throughout this course, right? We're just summing forces in the x, y, and the moments about point A, right? And if we do that, remembering that we're leaving everything in terms of x, we should get the following. So make sure you can replicate what I've done there with finding the axial force. Well, that one's easy, but the shear force and the bending moment. Now, just to point out at this stage, I have this function here, which is a linear function of x, and then I have this function, which is a quadratic, right? So immediately I can see that I'm going to have to draw some curves this time, right, with this. So then on the other side, when I deal with the triangle-shaped distributed load, I have a distance x from B. I've drawn it from the other side, right? I've drawn it from this side, back this way, rather than draw the left-hand side of the free body diagram where I cut it, just so that I've got less forces to deal with, right? Because the two sides should be equivalent. So I've drawn it from the right-hand side, called this point B over here, point C where I've cut it. This distance is x, right? So I've drawn my internal forces with the opposite directions, right? Because it should be equal and opposite to the other side. And then to find the area of this and how that it depends on x, like we did up here, we have to do half times the base times the height. The base now is so the total length of the wing 17.4 meters minus x, and then the height here is also based on x depending on where we cut it, right? So we get this as the area, it depends on x quadratically. And then again, same as above, we just apply the equilibrium equations to this sub-free body diagram to find the unknown axial force, shear force and bending moment. And now what I have is, so the axial force is always 0, right? And that should be obvious from the initial question again, because we have no parallel forces. All of the forces that we're dealing with here are perpendicular right to the wing. So in reality, if we have, so just a bit of an aside here, in reality if we have dihedral like the picture shows, then we're going to have some axial force, right? Because we're going to have components of this distributed load acting in this direction, but the way that the question simplifies it, we just have a perfectly horizontal wing with a distributed load and a weight vector. So that should be fairly intuitive to us that we don't have any axial forces in the wing. But this time, in the part where we have the triangular distributed load, we have the shear force as a function of x squared, so a quadratic, and then the bending moment as a function of x cubed. So we're just going to have to draw some slightly more advanced curves for our axial force, shear force and bending moment diagrams, right? So again, what we do is we just take note of what the shapes of the lines are going to look like. So linear, so straight line, quadratic, quadratic, cubic, and we just plug in some values, right? So the axial force, as we said, was always 0, so that's an easy one to draw. And then once we know, or once we've decided what our lines and curves are going to look like, we can plug in some values. So we use these equations that we found over here and plug in, okay, if x is equal 0, then v is equal to 465. If x is equal to 4.4, which is the upper bound for this cut, then v equals something different, right? So that's what I've done over here. I've plugged in the lower and upper bound for each of those cuts on either side, and then I've just made note of what the shape of those lines will look like. So this was linear, remember, because it just depended on x, and this was quadratic because it depended on x squared, right? So I've sketched out what that should look like. Now I wouldn't expect you to be able to draw those curves, right, these ones, in an exam or whatever, but if I give you a homework question or something with something like that on, then just use like a graphing calculator or Wolfram or something to plot that just to get an idea of what it looks like. Again, it doesn't need to be super accurate, you just need like the key pieces of information on here, where the maxima is, and where it crosses the x-axis or y-axis, right? So that just shows how the shear force changes across the length of the wing, right? So see that there's no shear force at the wing tip, and shear force is maximum at the wing root. And finally then, if we take a look at the bending moment, so we found over here that the bending moment between x equals 0 and x equals 4.4 meters is a quadratic shape, and the bending moment between 4.4 and 17.4 meters is a cubic shape. Well, again, I've just plugged in some values, found where it crosses the x-axis, where it changes, and it eventually goes down to 0 if we plug x equals 17.4 into this equation, right? We get 0. So the sketch should look something like that. And again, I wouldn't expect you to be able to plot that, you know, in your heads or whatever in an exam. So there we go. That's a slightly more complex version of the same thing. So today basically we've covered how to analyze the whole length of a member, or in this case a wing, right, to show how the internal forces change as a function of the length of the member or the wing. So that's it for today. Keep checking for updates and announcements, and I'll speak to you soon. Cheers.